What are compartment models? Compartment is nothing but grouping of tissues and fluids which shows same type of pharmacokinetic properties like blood flow and drug distribution. Hello viewers, welcome to my channel Pharma Talk with Imran. In this video we are going to explore a very interesting topic called as compartment models and their significance and use in studying the pharmacokinetic characteristics of the drugs. Compartment models are mathematical representations which are used to describe how drug moves through the body. That is, where the drug is going to absorb, where the drug is going to distribute, where the drug is going to metabolize, and where the drug is going to excrete. And now, why we use compartment models? These models are used to understand the drug interactions, and it is used to predict the drug concentration in the body, and it is used to simulate the process, that is ADME process, means absorption, distribution, metabolism and excretion, and it is also used to design the dosage regime, and it is also used to evaluate the bioequivalence. One compartment model. Here one compartment model, it is the simple and widely used model. According to this model, the whole body is considered as single and homogeneous compartment, and here the drug is going to distribute rapidly and uniformly in the body after the administration of the drug, and the elimination of the drug takes place at constant rate and it follows first order reaction. Means according to one compartment model, the whole body is considered as a single compartment or one compartment, when any drug is administered to the body, the whole drug is going to rapidly distribute and homogeneously distribute throughout the body, and it follows first order reaction. And what is the mathematical expression of this compartment model? Here Ct is equal to COE to the power of KELT, where Ct means what? It is the plasma concentration at the time t, and C naught or CO means what? It is the initial concentration after the dose, and e to the power of minus KELT means what? It is the elimination rate constant. Means here Ct gives the value of plasma concentration at the time t, means how much drug is present in the plasma at a time t, and CO gives the value of initial concentration when the drug is administered after the dose, what is the initial concentration, and e to the power of minus KELT gives the elimination rate constant. Here we can see a graphical representation of one compartment model. So when we see the curve, it shows a single exponential decline. So here we can see a single exponential decline. In the x-axis we have taken the plasma drug concentration, and in the y-axis we have taken the time factor. So here, because we are considering the whole body as a single compartment, the drug is going to rapidly distribute and rapidly it is going to eliminate. Okay, the next thing. So when we see this flow chart, when we have given the IV dose in the one compartment model, so here the entire body is treated as single homogeneous unit. So the entire body is treated as single and homogeneous unit, homogeneous unit. So here there is no segregation of the parts here. The whole body is treated as single one compartment. And then when we given the IV dose of the drug is going to distribute uniformly into this compartment, means in the body, in the whole body, that is in the single compartment, the drug is going to distribute in a uniform manner after the administration of the drug. Then elimination occurs directly from this compartment. So here the elimination occurs directly from this compartment, and the distribution is rapid. And the elimination occurs directly from single compartment. So these are the characteristics of one compartment model. Let us start about the two compartment model. So what is two compartment model? So in the single compartment or in one compartment, the whole body is treated as single compartment. But in the two compartment model, the body is divided into two parts. One is the central compartment and another one is the peripheral compartment. So in the central compartment, the highly perfused organs are included, like heart, liver, kidney. These are the vital organs and highly perfused organs which are considered in the central compartment. And the another compartment, that is the peripheral compartment. Here these are the less perfused. So here we are going to consider the muscle, fat and skin. So here we are considering muscle tissue, fat and skin. So this is about the central compartment and peripheral compartment. So when we have given the drug through the IV route, what happens? The drug is going to first distribute into the central compartment. The drug is going to first distribute into the central compartment. Then it is going to redistribute between the central and peripheral compartment. Then the drug is going to redistribute in the peripheral compartment, and elimination occurs from the central compartment only. So here we can see the plasma concentration versus time curve. It shows a bi-exponential decline. So here the distribution phase, which is called as alpha phase, then there is a rapid fall due to drug movement into the tissues, and in the elimination phase, that is beta phase, slower decline due to metabolism and excretion. So as we see in the single compartment, what happens there? The distribution of the drug is rapid and elimination of the drug is in a constant rate takes place. But when we see in the two compartment model, the distribution phase is called as alpha phase and the elimination phase is called as beta phase. Here the distribution is there is a rapid fall due to drug movement. There is a rapid decline in the rate of distribution due to drug movement in the tissues. In the first compartment model or in the one compartment model, the distribution rate is fast or rapid, whereas in the two compartment model, the distribution is slow because the movement of the drug in the tissues. And in the elimination phase, that is called as beta phase, there is a slower decline due to the metabolism and excretion. Here the elimination is also going to slow or decline. Why? Means due to these metabolic process and the excretion, there is a slow in the elimination in the two compartment models. Here there is a mathematical expression we have seen, we can see here, Ct is equal to Ae to the power of minus alpha t plus Be to the power of minus beta t. Here the AB point intercepts, they are called as intercepts, and the alpha is equal to distribution rate constant and beta is equal to elimination rate constant. Here we have taken the two constant factors, that is alpha refers to distribution, beta refers to elimination. So drugs with a significant tissue distribution, example digoxin, benzodiazepines. For these study, that is pharmacokinetic study of these drugs, we use two compartment model. Here we can see the graph for two compartment model. So here it will be like this. So here we have taken the plasma drug concentration, and here we have taken the time, and the curve is like this one. Compartment models in detail. So here it is used for the determination of half-life, that is T half, and CL, that is clearance of the drug from the body, and the volume of distribution of the drug in the body. So here these models are used for the study of pharmacokinetic characteristics of the drug. What are the pharmacokinetic characteristics of the drug? That is T half, that is half-life of the drug, then CL, clearance, and volume of distribution. Here T half means how much time taken by the drug to reduce by its half. Means when any 100, suppose 100 mg of the drug is given to the body, so how much time that it will take to reduce by 50 mg, or you can say to eliminate 50 mg from the body, how much time is taken by the drug. So here we have again the 100 mg drug and to the body, and it will take how much time to eliminate 50 mg, that is half of the drug from the body, that is called as T half. And it is also used for the prediction of drug concentration at time after the administration. So we can also predict by using these compartment models, we can also predict the drug concentration at any time after the administration. Then the next application is dose optimization in patient, that is therapeutic drug monitoring. So we can also do the TDM, that is therapeutic drug monitoring in the patients. Then we can also use for the design of controlled release formulations. These compartment models we can also use for the design of controlled release formulations. And by using these compartment models, we can understand or simplify the drug interactions and altered PK in diseases, that is pharmacokinetic characteristics of the drug. It will change in the disease condition. Here there is a summary which is useful. Here in the first column model is given, second column compartments are there, in the third column kinetics is there, in the fourth curve is there, and here the examples of the drugs. Here one compartment model, so here the number of compartment is single, and kinetics is mono exponential, that is we are getting the single curve, and here the curve is straight line, and it is used for the aminoglycosides drugs. And two compartment, so here there is a two compartments, that is central compartment and peripheral compartment, and it is the kinetics is bi-exponential, and here we are getting the biphasic curve. It is used for the drugs digoxin and diazepam. And multi-compartment, so it will we will see in the next video regarding the multi-compartment. So here we can see the difference table. In the first column feature is given, in the second column the one compartment model and two compartment model, or you can say we are going to differentiate the two both the compartments. Here the compartment, here in the one compartment model there is a single compartment, that is whole body is treated as single unit, whereas in case of two compartment model we are considering as the two compartment, that is body is divided into two portions, that is central compartment and peripheral compartment. And the distribution, here there is an instant and uniform distribution of the drug. Here initially there is a rapid distribution of the drug, but as the time went on, the distribution rate is becomes slow. And elimination, it is directly from one compartment, because we are considering whole body as single compartment. Here the elimination takes place from the central compartment. And the plasma curve, that is the drug concentration versus time when we are going to plasma concentration of the drug, and time when we are going to take the graph of this one. Here we are getting the mono exponential decline, that is like this one, and here we are going to get the bi exponential decline. Examples for the drugs, here we use for the aminoglycosides, here we are using for the digoxin and diazepam.